Okay. Hi, everyone. So, thanks a lot for giving me the possibility to present one of my projects that I've done with my supervisor, Chazal Bruckner, and one of my former colleagues, Esteban Castro. So, okay, Chazal already gave a wide introduction of quantum reference frame, so I will try to go directly towards the aim of our project. As you can understand from the title, quantum reference frame for Lorentz symmetry, we wanted to extend the quantum reference frame formalism in order to incorporate also Lorentz symmetry. So you can consider special relativity as the framework stem from the Einstein operational approach to space-time, which is based on how clock, ticking rates, and log Lorentz transform between inertial observers, right? So the first question that one could ask is, okay, what happens if then we extend the quantum domain to inertial observers, no? So, well, like simply one could ask what happens if I consider, for example, a superposition, a Lorentz observer in a superposition of velocities, so how this observer would perceive then the physical world. Then more precisely, how then would be the implied geometrical structure that comply with this extended notion of covariance, okay? So, okay, the next slide is a bit formal, but the only thing that I want you to enucleate from it is that first we wanted to use a covariance formulation of quantum mechanics, which has been already introduced by Carlo Rovelli, if I'm not wrong, in the 90s. It's a bit different, but it's basically very much alike. In order to avoid to refer to any preferred notion of time frame, we wanted to have a picture where time and space are treated somehow symmetrically in order to somehow better fit the requirements of Lorentz symmetry. So we incorporate somehow space and time coordinates in this so-called space-time cat, okay, in this way, where E of P is the positive square root of the relativistic energy. And then by linearity, we define so-called space-time quantum state. I forgot to say that we reduce the space-time to 1 + 1 dimension. And this generalized relativistic quantum state allow us to simply to extend somehow the initial condition of a state. We don't give a state lying on a simultaneity surface, but we can somehow localize the state in an arbitrary region of space-time. For example, in this moon-shaped region, which is basically the F support. Now, few features of this formalism. If we do the pairing of these two space-time cats, we get the propagator for positive energies. Then if we project on T prime X prime the space-time quantum state, we get the standard notion of a relativistic wave function, which comply with the positive square root of Klein-Gordon equation. And we recover also the standard Klein-Gordon inner product, if we do the inner product of these two space-time quantum states. Maybe the last thing is, okay, how these space-time quantum states behave under the action of a general Lorentz transformation, and they behave exactly as we could expect. The space-time coordinates transform accordingly to the Lorentz boost, so they are hyperbolically rotated. Okay, so if we jump on top of this flying rocket, what we would see is this hyperbolically rotated, boosted, moon-shaped region of space-time. Okay, and now in this slide I will try to briefly explain how we build this prescription to jump from one relativistic reference frame to another, from one system to another. Okay, we have to keep in mind that one mantra of quantum reference frame formally is that every physical meaningful statement is relational. So in a very simplified example, I'll give you a state describing my physical landscape, free particles, okay? And this is given according to one Lorentz perspective, okay? But I want to achieve a fully relational description in order to describe one particle with respect to another system, for example. So we achieve this sort of fully relational perspectiveless state formulation, simply making the state invariant under the action of global Lorentz transformation. From a group theoretical point of view, this means applying the G-twirl of the group, so integrating all over the possible Lorentz transformation of the state. So now we have this Lorentz perspectiveless formulation of the state. And then what do we do in order to take the perspective of one of the internal system, one of the particle, for example, C particle? More or less, as Chasla explained, we have this control Lorentz transformation on the state of C particle. We read basically the state of the momenta, and then the velocity and rapidity, and then we transform accordingly the rest of the systems.
Sorry, this integration that you're making, does it converge? I mean, it's not compact, no? This group, or?
No, it does converge. It does converge, yes. Yeah, at least for one-dimensional 1+1 space-time, I'm quite sure there's a result that says that.
What are you integrating there?
On the rapidity. Okay. Rapidity of is the parameter of the Lorentz boost.
From 0 to infinity,
minus infinity plus infinity. Okay. Yeah, I mean, but yeah, no, but. Right. So what we get from here is the state from the perspective of C. Interestingly, the interesting thing is that the state of C now is factorized out, so there's no relational quantity between C and the rest. And we can simply trace it out, to give an intuition that there's no somehow mathematical physical content in it. Omega C is simply the full superposition all over the possible momenta of C, so basically full indeterminacy. And we can do the same for A, no? So then the transformation that would guide me from C point of view to A, it's simply the suitable composition of those maps, which gives us back exactly what Chasla presented before. Okay, so now we have the mathematical tool that would allow us to jump from C to A, from one relativistic quantum reference frame to another one. And then let's apply it to simplified scenario. Okay, so now we have a state from the perspective of the guy sitting on the ground, describing a rocket in a superposition of sharp value of velocity, for example, and FB space-time quantum state describing this moon-shaped state, okay? And now we're going to jump on the rocket, and what we can get, as we somehow could expect also from Chasla's presentation, is an entangled state, where in each branch we have a different boosted moon-shaped region, okay? Now entangled with the previous relativistic quantum reference frame labeled by C. Okay. Another somehow interesting example, somehow which refers more to a standard case where we somehow locate the state in a simultaneity surface of C. What happens if we perform the jump is that there is a resulting state. We have a superposition of tilted space-time slices, which are not anymore simultaneity surface for the rocket's pilot. Right. Okay, another feature that is worth to be discussed is the analogy, what comes from the analogy of active and passive representation of the transformation. We can picture in the active wave this state keeping fixed somehow the space-time frame and having the superposition of the differently boosted moon-shaped region, or equivalently, we can keep fixed the space-time volume, this moon-shaped region, and express the superposition in terms of the space-time frames, right? Okay, and now these are the last two slides. Here, we try to recover the standard phenomenology of special relativity. I can good with time, perfect. So the scenario is basically the same. Okay, we describing this physical landscape from the point of view of the guy sitting on the ground. We have a couple of point-wise events, which according to this guy, they have a separation in time of delta t, t2 minus t1, okay? And now, what happens if we jump on top of the rocket? Okay, now we don't consider the entangled state, the state of the reference frame C. We just focus on the state of the clocks. We have an entangled state. In each branch, we have a boosted couple of the previous event B1, B2, which now have a time separation, which is a special relativistic time dilation, okay, according to the gamma factor for the blue branch, gamma of omega pi 1, which is related to the velocity of the blue space shuttle, and the same thing for the other branch. Okay, so we can infer basically that the rocket's pilot is observing a superposition of special relativistic time dilations. And then we can basically say the same for the length contraction. Okay, now somehow the setup is a bit more cumbersome because of the complication of performing a measurement of rod lengths. But basically, it's very similar. Again, we start from the perspective of C. We have two couple of point-wise events, moon-shaped and atom-shaped, which they have a space separation which coincide with the length of the rod of the guy sitting on the ground. And now the velocity of the rocket is related to the ratio between the space separation, delta TB over delta X for VB, and delta TD over delta X for VD, for the yellow speed, okay? And this is why, because once we perform the jump, we're going to obtain in one branch of the entangled state a couple of events which lie now in a simultaneity surface for the rocket's pilot. So we can somehow perform the measurement of the length, which is going to be a spatial relativistic contraction of the rod length of the guy sitting on the ground, and the same for the yellow branch. Okay, so also in this case we can infer that the rocket's pilot probes a superposition of spatial relativistic length contractions. Okay, so this is basically all the somehow extended phenomenology that we probed with this in this extended framework. So let me summarize a bit what we did. We started from the basic question of like extending what we know about Lorentz covariance if we allow an inertial observer to be described by a quantum state. First of all, we use this new picture. Okay, it's a different picture for a relativistic quantum system, which allow us to have this general space-time representation of the state, not referring to any preferred time frame. And then, thanks to it's called sort of quantum Lorentz transformation, we can perform this change of perspective, obtaining all the consequences that we already seen. So superposition of space-time frames in a sense, superposition of spatial relativistic time dilation, and then contractions. Okay, so this is basically summary of this work. And then for future prospects, this is basically one small piece of work which is cast in a choral somehow effort, no, as Czesław said, in order to better understand the interplay between quantum mechanics, quantum domain, and space-time geometry. An interesting thing would be somehow to give a complete prescription of what could be a sort of quantum chronogeometry, no? What would be geometrical sense, what would be the geometrical structure which has this extended notion of group of symmetry group, sorry. And of course, another interesting thing will be to extend this framework to a field scenario. And this is basically everything that I wanted to tell you about.
Thank you, Luca, for your talk.